Okay, good morning, everyone. Welcome to one of the first paper sessions of our conference. This topic here is Intro to Innovations in Video Encoding. I'm John Furter from Quest US, SMPTE Fellow and Governor at Large. As usual, if you're going to have questions to ask, and there will be time for questions, we just ask that you identify yourself and your company affiliation, so that our presenters know who they're talking to. So we have three very exciting papers today. I'm very, very happy to be chairing this session. The first paper, as you can see, is the new JPEG XS TDC profile. And it is being presented by Jean-Baptiste Laurent, who's the Director of Sales and Marketing at Intopix SA. So this session is going to delve into the upcoming third edition of JPEG XS, otherwise known as ISO IEC 21122, which introduces the temporal differential coding profile, which builds on the JPEG XS High profile by integrating wavelet-domain temporal differential coding, a technique that minimizes correlation between successive video frames, especially in static regions. Jean-Baptiste joined Intopix in 2007. He holds a business engineering master's degree from the Louvain School of Management in Belgium. Jean-Baptiste.
Thank you. Good morning. So as said, so JPEG XS TDC, you are probably familiar now with JPEG XS as it has been created a few years ago. XS is one of the standards of the JPEG committee. XS was chosen as a kind of a nickname for extra small, extra speed. And the TDC, as just explained, is the meaning is temporal differential coding. One of the purpose of the JPEG XS codec is to help to manage more pixel, to transport more pixel, to store more pixel, but with that in mind, to reduce also carbon footprint and power consumption in devices and workflow. So the main objective of JPEG XS when it was created was to deliver codec with lossless quality. I would say lossless quality for human visualization, but also for machine vision. That technology is also presented in the automotive world, for example, but also to produce always constant quality as we expect in production workflow, and to minimize the complexity. So it's a codec that has been made to be low power, to consume as less memory as possible, highly parallelizable in software, and to address all the processors that exist today, from FPGA to CPU to GPU and to ASIC. Why it's low complexity? It's a codec that offers an extremely low latency, so it's only bufferized few lines of pixels. So implementation available today goes down to 10 video lines to encode, 10 video lines to decode. That was the objective of the first call of JPEG XS in 2017, if I'm correct. The JPEG XS also wanted to be an ISO standard, so with open specification to address a situation in the industry where there was emerging technology, lightweight compression, that were not standard based. So today it's really the first lightweight compression standard created at ISO to replace uncompressed video. So where it's used today, where is it leveraged in the media industry? So JPEG XS is seen as a new SDI. So it's supporting both the SMPTE 2110 standard and SMPTE 2022-2 standard to be efficient both in local area network, in studio, in facilities, in stadium, but also over wide area network for remote production and cloud-based production. So you have FPGA-based product, you have software-based services and solutions, it's also a good path. That's what we saw over the last years to not just to support the transition from SDI to IP, but also from HD to some 4K workflows, as it's bring a lot of efficiency there. So I will not go over all the standards about JPEG XS existing in the industry, but you have RTP packetization, transport stream packetization, and in transport you see JPEG XS being used with all the, let's say, traditional 2110, 2022, but also SRT and RIST. The container that exists for JPEG XS, the formats, the standard are covering all the needs of the media industry. So the standard has a different part defining the coding, the profiles, the colorimetry. There are transport standards existing at SMPTE, at VSF for RTP, transport stream, but by extension for IPMX, SMPTE 2110, ground to cloud, cloud to ground workflows. It's part of NMOS protocol. And if you need to store, this is like the other codecs, you can create an MXF file, an MP4 file, and you have the GXS, that is the image extension format for it. So a bit of history. So this presentation is about the edition 3, but the edition 1 is probably the most popular today in the media industry, with the definition of the high profile that we can find in 2110. For example, it defined 444, 422, compression up to 12-bit, and other profiles such as main and light that are less used in our industry. It's constant bitrate codec, so that you have some more always the guarantee if you use JPEG XS as a mezzanine format for transmission, that you get exactly the budget that you expect in your network. The second edition has brought additional profiles which are not yet used massively, but you have 420 profile that was a need in IPMX standards, for example. But you have also raw Bayer compression. It's kind of unique in the landscape of standard codec. So within the MPEG or JPEG committee or other committee standardizing video compression, JPEG XS RAW, it's the first ISO standard for raw Bayer compression. That was part of the edition 2. And with edition 3, we set a new goal for the JPEG XS to look at how we could further extend the compression efficiency. There is one part that did focus on mathematically lossless up to 16 bits. So previously mathematically lossless coding up to 12 bit was already available. Now you can address 16 bit. But the part that is essential here in this presentation is the temporal differential coding. So the addition of a new frame buffer for the TDC profile that is compressed, that has some refresh mechanism. So adding into a JPEG codec, in fact, an inter and intra mechanism. So the status of that edition 3 is that the part about the coding, the profiles are already available, but in the reference software will be available early next year. So this is a summary about what I just said. So the TDC is offering up to 50% of additional compression efficiency with graphic contents, Excel spreadsheet if you want, or more CGI desktop content where you have some static content that gets repeated from frame to frame. So if we look at the promise of JPEG XS, so it's we could say an evolutionary concept. We have still with the new TDC profile maintained the promise of low latency, high quality, all platform support and low complexity, but we increase the compression capability. So the call for technology that was initiated at edition 1 was asking if we could run, for example, 4K 60 encoding and decoding on an Intel 7 processor, generation 8, so from 2018, or we could put a 4K 60 encoder-decoder in a lower range of FPGA from Xilinx, AMD, or Intel Altera. With the TDC, we continue to look at this challenge and say, okay, now can we continue to do more to achieve more efficiency, but still maintaining the DNA of that technology, which is low complexity, low power. So the TDC profile, I'm too small to look at my screen here, but in details, it's introducing wavelet prediction without any motion compensation like MPEG type of codec. So we want to keep the complexity low, and we don't want to introduce additional latency. So the 10 lines of latency that we have to encode or to decode, we want to preserve that. So we have and we don't want to bufferize too much at the cost of impacting the complexity and latency. The introduction of frame buffering is a way for us to increase compression efficiency by looking at the difference from the actual frame and the previous frames, but we don't want to use too much DDR memory, so we have a compressed frame buffer that is encoding driven, so we can even control the level of compression that we apply to that buffer, so that we can reduce the bandwidth to the memory for the codec. And at every frame, we have a mix of inter and intra-frame coding. So this is kind of new as well. So some part of the content that has of the frame that has some motion will be coded in intra, but part that gets repeated will be coded in inter. And this is not achieved with a spatial resolution, it's achieved in the wavelet domain. So we have a refresh mechanism that is cyclic, so we can refresh at different level of wavelet subbands also. So you see the impact that it has on the compression algorithm. One thing that is positive is that we preserve also backward compatibility with high profile encoding, so the one of edition 1. So the TDC somehow supersede with still the capability to decode intra-only compression. So in the edition 1, we had the goal of performing good objective measurement and subjective measurement. And for subjective measurement, we apply the near-lossless quality assessment standard, so the ISO IEC 2970-2, where one side of the screen is uncompressed and the other side is interleaving compression and uncompressed images, and we asked to the audience if they were able to distinguish which side of the screen was the compressed one. We applied that using various type of contents, and at that time we were going down to 3 bit per pixel, which is, if you have a 10-bit 444 content, this is a 10-to-1 compression. If you don't have the reference frame, it's a wavelet scheme. We showed that 4K 60 over 1 gig was achievable with natural content. That was easy to compress most of the broadcast media content. But when we had some desktop content, this was more challenging to compress more. So we looked at a way to compress this type of content. So you take at Intopix, we call that the killer sheet. So you take an Excel spreadsheet, you change the color of the fonts, you could change the color of some layout of some of the cells, and you try to compress that. With the high profile, trying to achieve that below 3 bpp was extremely difficult, or I would say impossible to be visually lossless. By adding the TDC coding, we solved that challenge, and that we retrieve in every desktop content, CGI, KVM type of application, or gaming, where a part of the content gets repeated over multiple frames. So that's really what the TDC brought up. So what does it mean in terms of compression efficiency? So today, using TDC, we've been showing up that everything gets possible in a really reasonable network infrastructure. So new laptops having the last generation of processor have all 2.5 gigabit Ethernet interface. I am able to achieve 8K 60 below 2.5 gigabits. So if you look at the uncompressed throughput, like about 60 gigabit per second, now I can go at about 2 gigabits and be visually lossless on this type of content, even if I have the worst case screen content scenario. Of course, 8K is an extreme example. You don't use 8K every day, but it's just to illustrate the benefits of it. And of course, I want to highlight that because we did not highlight that too much in the past, but you can further optimize the bandwidth of the network with JPEG XS as it's a wavelet codec. So we can reduce the power consumption of processor, we can and infrastructure, but we can also further optimize the bandwidth in low latency workflows thanks to the wavelet scalability of JPEG XS. So by at the encoding level, I can design some encoders that leverage the wavelet scalability to create directly a proxy streams on top of the primary stream. So I can now send without additional latency 50 or 100 megabit stream instead of a gigabit or 500 megabit stream, as illustrated in that diagram. On the decoding level, if I get a JPEG XS stream, I can decode HD resolution directly from a 4K code stream. For example, if my processor is limited in my computer, or if I need to decode a lot of stream in a multi-viewer, I can further optimize my power consumption, my processing requirements. So now about the quality analysis. So we compile in our paper several analyses on desktop content. So here, for example, you see some gaming or e-sport or graphic animation type of content. You can see the benefits of JPEG XS TDC compared to JPEG XS High, or for example, here you see already the PSNR was already good on a high, but moving from TDC on this kind of gaming content, we were able to rise up the bar. You see on this static natural content, it was also significant, the benefits of it. I can show you on natural content also, so if I have some content where everything is moving, I cannot really get benefits of the temporal differential coding. Well, you see that TDC and high are pretty much at the same level as coding profile. So high is intra only and TDC has the benefits of inter and intra. But here everything is moving. There are motion panning. But on that waterfall here, I have some part of the content that is not moving at all, but the waterfall is obviously moving. And you see here that I have an increase in coding efficiency using the TDC profile. If I show you that on a more extreme content, so I compile at high 1.5 BPP is like 4K at 4K 60 at 750 megabits. So I'm below 40 dB, which is not really good. If you're familiar with PSNR metrics, typically when you have like 35, you will look at that content with your eyes. And by moving to TDC, now I go above 50 dB. So it's a significant improvement. So I move from 35 to more than 50 dB. And you see in how many frames, thanks to the refresh mechanism of the TDC, in just a few frames, I'm rising up to that PSNR. You see the same kind of effect on the other content where you have some of the windows that are even moving over the desktop. So that's about the quality, but as JPEG XS has also a promise of a low complexity, low power, we also look at into PIX on the implementation impact of adding the TDC right now. So it's pretty new, so we know that we will further optimize that in the future. But one of the original question, so in 2019, was about achieving 4K 60 on a regular i7 processor. So that's a quad-core processor that is pretty old already. So we see that it consumes a bit more than our high-profile implementation, but we still achieve extremely good performance in both HD format or 4K format. And we know that it will improve across time, of course. And on the FPGA promise, so we really want JPEG XS to help to reduce carbon footprint, to help reduce power consumption. We know that FPGA are keys in that challenge. JPEG XS TDC offer excellent logic optimization in FPGA. It requires slightly more logic, but remain pretty compact to go over these more cost-effective FPGA. So we at Intupix implement JPEG 2000 for during 1 decade. For example, it's being used in cinema, in the DCI projectors, for example. We see that our TDC implementation, even if it adds the additional temporal differential coding, is still 3 to 4 times smaller than what a JPEG 2000 codec is able to offer. And we know that what drives the power consumption of these FPGA design is the requirement for additional DDR memory. So with the TDC profile, we need DDR memory. But as we do all the transfer to memory via frame buffer compression, and that frame buffer compression is even adjustable, you can see for example, the amounts of memory, external DDR bandwidth that we need if we set the frame buffer level to 3 BPP or 12 BPP. It's significantly lower than codecs like JPEG 2000 in Intra that was requiring frame buffering for the encoding, for example. So we know that the codec still achieve up to 10 times power reduction compared to JPEG 2000 and enable even develop a power over Ethernet device, which is also very convenient. They have some constraint on power consumption and extremely low power design. I'm not speaking even on the impact on ASIC design, but you can directly understand that from that slide. So in terms of conclusion, we see a continued evolution with the new JPEG XS TDC profile. It still delivers the key benefits of JPEG XS as low latency, low power, high quality compression to replace uncompressed video, efficient software and hardware operation, and the new TDC is very good for static and also natural content. It maintains somehow the capability of backward compatibility. So existing JPEG XS High encoder will be able to be decoded by new decoders adopting TDC, and TDC encoders on the field will be able also to generate high profile or TDC to preserve future interoperability. So we invite you, if you are here tomorrow as well, to stop on the Interpix booth. So we have an implementation of TDC that we are showing up, and to see the standard in action. And we have some uncompressed pralines. If you don't like compression, we have that as well. Thank you.
So we do have time for one or two questions, and I apologize to the technical. There you are. Thank you. You read my mind. So please step up to this microphone, and please identify yourself and your company affiliation.
Thank you for the talk. Jens Ohm, RWTH Aachen University, Germany. So what kind of wavelet transform is used in JPEG XS?
It's a 5.3 filter, and we have two vertical. I mean, it depends on the profile, but in this high profile in TDC, we have two vertical decomposition and up to five horizontal decomposition.
So it's the same as in JPEG 2000 for lossless mode, right? To 5.3. I think so, yeah.
That exists. The 5.3 filter is the same, but the number of
So I have not looked at it a long time ago, but so the 5.3 low-pass filter is not a very good anti-aliasing filter, according to my experience. So does this cause, if you use it for spatial scalability, may this cause some problems if content is moving? Because if content is moving, then the subsampling position changes over the video, and sometimes this leads to temporal artifacts because the subsampling position is different in subsequent frames. It may not be too critical if you take 8K to 4K, but if you take, let's say, 4K to HD, it may already become visible.
You speak here about the scalability effect. That's what you mean about
scalability together with moving content.
Okay, so I would say first on the 5.3. So 5.3 is in terms of complexity, it's a very efficient transform compared to the 9.7. So there is a reason why JPEG XS picked that one. It's for the low power, low complexity effect of it, and also for the quest of compression efficiency. That's the target of JPEG XS. It was really suitable for that. For the motion and quality, I really invite you to come to see the demo, because you will see that with your eyes, and that's, I think, that's the best.
And at this point, we have to move on. So Jean-Baptiste, thank you very much.